All right, here's a video where I'm going to walk through several topics to try to get to a behavioral implementation of a 7-segment display. So the first thing I'm going to start with is wires versus registers. We'll talk a little bit about that. There's some subtleties behind how we do this in Verilog. We're not going to go into all the details yet. We'll evolve that as the course progresses. All right, the next thing I wanted to do is cover 7-segment displays, because a 7-segment display is used in many types of digital systems. We have we have a set of 4 7-segment displays on our Basis 3 board. So we're going to learn about the steps involved with using those and writing Verilog descriptions that implement into hardware to drive a 7-segment display. All right, and next, the way we're going to do that is with a different type of implementation in Verilog that we haven't seen before. We're going to look at a behavioral implementation of a 7-segment decoder. So let's get started with these 3 things. All right, so the first thing, let's talk about wires versus register. He calls it, in Verilog, it's reg. All right, so we've used wires. We used wires to connect input and output ports of modules together. The thing is, a wire must be driven by something. It can't store a value without being driven. So what does it mean to be driven? It means, you have to have some circuitry that connects to it that actually makes it take on a value. So if you just have a wire by itself, just like a physical wire, it can't take on a voltage unless unless you hook it up to something. Okay? So, some restrictions on wires. Wire elements cannot be used as a left-hand side of an equal sign, or we have 2 different equal signs we haven't talked about yet, but you can't use those on the left-hand side of an always block. We're about to use always blocks. Okay, wire elements are the only legal type in an assign statement. We've used a lot of assign statements. We're assigning a wire element to a certain connection in Verilog. All right, so those are things we've done so far with wires. In our behavioral description, we're going to use always blocks. Reg variables are similar to wires, but they can be used to store information. It says like a register. Well, we haven't covered registers yet, but we will be covering those soon. And so we're going to use those because we want to use an always block. So it turns out the reg is the only legal type or variable that can be on the left-hand side of an equal sign in an always block. Okay, we've already used initial blocks, and when we did our simulations, we started out, we declared some registers, and then we set those values, and we could do that because they're registers or reg variables. They can take on values in a simulation, and so that's what we've done so far. All right, so I just wanted to point that out. The next thing I want to do is take a look at a 7-segment display. So you've seen these before. A 7-segment display literally has 7 segments, and we label those as shown here, where we start at the top and we move around in this clockwise manner and then end up in the middle. Okay, so the element or the LED names are A, B, C, D, E, F, and G. Okay, in our particular Basis 3 boards, the LEDs turn on in a low true fashion, meaning it takes a 0 to make that particular LED element to light up. All right, so what I've got showing here is an example. Let's say we wanted to make a B, all right? And so what our hardware is trying to do is to take data, all right? So how would we represent B? B is 1, 0, 1, 1, okay? And we want to take that and turn it into a bit pattern that represents the letter B in a 7-segment display. So I'm looking at this, the places where the LED is lit up, the part that I'm showing in red, should be a 0. So I have a 0 at F, I have a 0 at G, I have zeros at E, I have zeros at C and D. The only place I don't have zeros are for elements A and B. Okay, so this is just the way, these are in reversed order. This is just the way these are mapped. With the notation that we use in the basis 3 boards, okay? All right, so what I want to point out next is that you could represent this in hex because it's a little easier to check your work. It's hard to see bit patterns. We've talked about that many times, but if I break this up into hex, this would be 0, 3. All right, so the next pattern I wanted to talk about is a 6. All right, so with a 6, we need to distinguish between a 6 and a B if we're going to represent all the hex digits. Okay, 6, we put a tail or a thing on the top so that it doesn't look like a B. All right, so if we had that, then what is our code? Well, we can go back and we can say, well, I have all the same segments are off, but so is A. The only thing that's not on is B, and we put a 1 there whenever B is equal to an off position. Okay, so of course we convert this to hex and we get 2. All right, and one more example. I'm going to do a 9. Typically, we would put a little tail piece on the 9. Okay, and so the segments that are on are everything except E. So zeros are on, and E is off. Okay, so I convert that to hex, and that would be 1, 0. All right, so that gives you an idea of how the digits work. And so what we're doing is we're decoding. We're taking this data, this 4-bit data, and we're turning it into 7 bits so that we can drive a display. Okay, of course for 6, this would be 0, 1, 1, 0 gets converted into this number. And then finally for a 9, 1, 0, 0, 1 gets converted into this number. Okay, well, how do we write Verilog code for that? This is actually something you could do with gates, right? You could make a big truth table. All right, the truth table would have A through G as columns, and then we'd have all the minterms 0 through 15, and you could do the 7 different Carnot map minimizations to come up with the logic function that would drive the 7-segment display. Now, fortunately, we have Verilog and HDL tools that will let us do that synthesis where we don't have to go through the tedium of making all that happen. Okay, so let's talk about that now. I've got some artifacts here. Let me get rid of these. All right, so here is a module that we're using to do an implementation of a 7-segment decoder. So we're taking the hex digit as an input, so it's 4 bits, and we make these 7 bits of output, 6 through 0, 3 down through 0 for the input. All right, so here's what's different. This is a behavioral code, and one of the things that Verilog can do is it can take code descriptions to do a simulation of how a circuit should work. So you can develop your design that way. And then it's also possible, if you write the code in a good way, it's also possible to take this behavioral simulation or behavioral description and let the tool come up with the equivalent hardware implementation. Okay, so anytime you have something that's basically can be written as a table, it's pretty easy for the tool to synthesize that into hardware logic. All right, so that's what we have here. This is a new thing, but it's got similar features where we still have a description of a module. We put in parentheses, let me highlight that. We have parentheses defining our input and outputs, and then we start with an always statement, okay? Now, one thing that's different with an always block is, and we haven't used always blocks before, there's a sensitivity list that's associated with an always block. And so you'll find that sometimes within an always block, you don't need to be sensitive to every variable, especially when we start doing sequential designs. But let's defer that for now. What you need for now is to know that with the at symbol, we have the at symbol with an asterisk. The asterisk means every variable that shows up here is in the sensitivity list. We'll talk more about sensitivity lists as we go through the course. All right, so for now, just accept that you're going to have to, with this always block for combinational logic, you need every variable in the sensitivity list, and this is just a shortcut to put that in there. Okay, the next thing is we're introducing a new type of description, and that's the case statement. So the case statement is great for truth tables. All right, so what we're doing here, it's very much like a case statement in MATLAB or in C. Some of the notation's a little bit different, but you give it the input of the case statement, okay? And notice there's a case and then an end case. Because of that, you don't need a begin and an end. It takes care of parsing that within the definition of the case statement. All right, but then you give it the input variable. So our input variable was num. All right, and so num is 4 bits, so we can assign all the different 4-bit combinations. Okay, so we take all the 4-bit combinations, and the left-hand side of the assignment has to be a register. Okay, so that's the key thing here. If you didn't put this reg declaration, you would throw errors. Okay, so you're driving, in this particular case, when you get this input condition, SSEG is assigned to this set of bits. All right, so it's not hard to work through all the combinations, and this gives me all the 16 different combinations that I need to represent hex digits. All right, so I'm going to give you this code, and that's going to be one of our modules that we use for Lab 6.